Hi, I'm Jim. Today I'm KQ8E. When I first started in ham radio, we had a class of license called Novice, which was only good for 1 year. And since I was in Pennsylvania, I got a 3 call. And at that time, this was 1957, you got an N in your call letter to indicate that you were a novice. And that license was only good for 1 year. So within that year, I became a general. And a few years later, I moved to Ohio. And at that time, when you moved from one call district to another, you had to get a new call. So I became W8GMG, and that call has been given to another ham today. And I left my call run out, got busy with life, and got out of ham radio for a while. And when I decided to get back in, I managed to do it as an advanced operator, and then went to the extra. So that's been my call letters through the years. Now recently I rejoined my local ham club and found some of the guys there working what they called FT8. So I thought I would try that. It sounded kind of interesting. And once I got set up and on the air, within the first 3 hours I had worked 14 countries. And this seemed kind of easy to me, too easy, in fact. So I kept playing around with the FT8, and within 37 days, I had worked 100 countries. It was kind of like shooting fish in a barrel. Now, I was using 100 watts or less every time, and I was using simple dipole antennas. So nothing special, and I'd be interested to hear if anybody has made 100 countries in even fewer days. I bet there has been. Maybe you could leave a comment below if you've done that. So at any rate, I thought, well, maybe there's ways to make this harder and more interesting. So I decided maybe, since you can do FT8 on low power, maybe I should convert my station to solar power. And I'll show you how I went about doing that in the rest of this video. Also, since FT8 works with low power, and I've always been interested in antennas, there's a lot of possibilities there for easy low power antennas. And maybe a loop antenna for 160 meters. Again, since we're on low power, that shouldn't be too hard to do. So I plan to do a video on antennas in general, and particularly on this 160 meter loop that I plan to build. So stay tuned, subscribe, and we'll be covering a lot of different subjects in the future. But let's go to the solar battery part of this video now. Well, if we're going to battery power a station, we got to know what all is in the station and what the loads are. And what I would need to power is, of course, the computer itself. The rig here is a TS2000, and then here is the signal link USB, which is the interface between the computer and the radio. And below that I have an antenna controller which controls the action of my dipole antennas. And if you're interested in more information about that, there's an article about it in the September QST from 2008. And also one of the dipoles that's controlled by that is rotatable, so I will also want to operate that antenna rotator from the battery. So the first thing to do is to find out how much current all of these things draw. Okay, here's the breakdown of the loads in my ham shack. The TS2000, when it's in the receive mode, draws 2.37 amps. And when transmitting at 5 watts, it draws 7.75 amps. At 10 watts, 8.8 amps. At 20 watts, 10.1 amps. At 50 watts, it's 12.3 amps. And at 100 watts, it draws 15.4 amps. So now at least I know what kind of power I'm going to need during receive and transmit. Now my antenna controller, my rotatable dipole covers 5 bands. And on the first band, my antenna controller draws 1/10 of an amp. And when I get up to the 5th band, it's drawing 0.38 amps. Now I plan to run the computer and the dipole rotator from an inverter. And I picked a 400 watt inverter, which should be overkill. So at no load on the inverter itself draws 0.38 amps. And when I boot up the computer, it draws up to 6 amps for a while. It's not the computer itself, it's the current into the inverter. And when the computer is booted up and running WSJTX software, the inverter is drawing about 2.5 amps. Now when the rotator is turned on but not turning, it causes the inverter to draw 0.88 amps. And when the rotator is actually turning the antenna, the inverter will draw 2.8 amps. So the inverter has to supply momentarily this 2.8 amps and momentarily 6 amps. But during normal operation, the current's much less than that. So the next thing, let's look at how solar panels actually work. The last thing that I just showed you was the rating label for my solar panel. And these are the things that are listed based on a solar flux of 1,000 watts per square meter. So the maximum power the panel will put out is 100 watts. And the open circuit voltage at this radiation intensity is 21.6 volts. So if you just put a voltmeter on the output wires of the terminal, at this radiation level, you'd get that many volts. And if you took those leads and shorted them together, you'd get the short circuit current of 6.5 amps. Now the 100-watt rating occurs with a voltage of 18 volts, that's this point right here, and a current of 5.56 amps. So that's the maximum power point. Now if on a cloudy day where the solar radiation is less than 1,000 watts, then your current capacity comes down roughly proportional. So here we might be at 3¼ amps, and here we might be at 1½ amps, something like that. But it behaves pretty much as a constant current source until we get out here at the very end. I decided I needed two 100-watt panels, so here I've strung them together with some aluminum angle, and I'm going to make them so they can be hinged so that the angle can be changed during different seasons of the year to maximize the sun angle. And I'm going to take each panel's electrical output back separately so I can decide later whether to put them in series or parallel inside the shack. Okay, here's the two solar panels mounted on the roof of my ham shack. And they're up off the roof to help keep them cool. They work better the cooler they are. And as winter approaches, I'll put a strut in the back bracket there to raise the angle of the solar panels. And while we're here, here's a quick shot of my rotatable dipole. So the wires from the solar panels are pretty short. They go into the ham shack right over there. So I didn't have to use Gigundi wire. I think it's number 12 wire. Okay, here is my control panel for the charging system. And this is what's called an MPPT controller, which stands for maximum power point tracking, as opposed to a PWM type charge controller. So the MPPT type will get more charge for a given set of conditions into the battery than the PWM type. But these are a little more expensive. This one was about $100, and you can get PWM types that are much smaller and maybe in the order of $25 to $30. Here's my 400-watt inverter. I got this from Harbor Freight. And also I have these little voltmeters here. I got these on Amazon. I think there was 5 of them for less than $10. So this one will be reading the voltage output of the solar panels, and this one will show the battery voltage all the time. And these little things draw about 10 milliamps. So this is where I'll connect the solar panels. Right now I'm set up to have them in parallel. This is where I'll connect accessories such as my antenna controller. And you may have some different kinds of accessories. And the battery will connect here. And since these kind of things often work at different battery voltages, like this one is good for 12 or 24 volts. You're supposed to connect the battery before connecting solar panels so that the unit knows what voltage to configure itself for. Now this panel here is wired so that this is where I will plug in my computer. And when the switch here is in the up position, that outlet is wired to the output of the inverter. But when I want to shut down the ham shack, I turn that off, and the computer will be connected to the normal 110 volt input. And this top outlet is permanently wired to the 110 volts in case I want to plug in some AC device. So also the switch turns on power to the accessories out here from the battery. So that's pretty much the rundown of the panel. So I will go install this, and then we'll begin to see how things work. Well, here's the solar control panel mounted on the wall. And two things I forgot to mention in the last clip. The antenna rotator will plug in here. And the charge controller comes with a temperature sensor. The temperature sensor plugs in to a socket down here. There's nothing in the instructions about what to do with it, so I plan to tape it to the battery. And the charge level of the battery is a function of both its voltage and its temperature. Also, another thing I'd like to point out, I have the batteries setting on some styrofoam. The floor here is concrete, and whatever you do, don't set batteries on a concrete floor because that'll cause a temperature differential throughout the battery. It'll be cooler on the bottom as the concrete sinks away the heat. And batteries don't like a temperature differential across them. So at least put them on wooden boards or in some way insulate them from a concrete floor. Okay, here I've installed a 30 amp fuse at the midpoint between the two batteries. And this is the normal cable that feeds the transceiver itself, and these fuses come with that standard cable. So here we can see the battery voltage, and this one's showing the voltage of the solar cells. Now we're at 7 o'clock in the evening here. The solar cells are in the shade, so although they're putting out 16 volts, I'm sure they cannot put out very much current. We may be down into a half an amp or less at that kind of a light level. So there's the installation, and the next thing is we will run this. I need to wait for some daylight to charge things up thoroughly, and we'll run some FT8 and see how the batteries work. The terminals on the right here are where you're supposed to connect your load, and the idea being the controller will disconnect the load if your battery voltage goes too low, which is considered like 10.5 volts. Now I plan to be my own monitor. I can see the battery voltage and cease operation if it's getting too low. And the higher you keep that lowest voltage, the more cycles the batteries will be good for. So the less you discharge the battery each cycle, the more cycles it can work over. And by the way, I think I forgot to mention, these batteries are actually 6-volt golf cart batteries, and I have them connected in series to yield 12 volts. And they are rated 240 amp hours each. And of course, if you don't fully discharge them, you would get less amp hours per cycle. But I think we have plenty of amp hours here to operate several days without any sunshine. And that black spot there is where I tape the temperature sensor to the battery. Okay, we're pretty much set up and ready to operate. And I can lean over here and keep an eye on the battery voltage. And the one thing that I really don't like is the transmitted tone coming over the speaker of my transceiver. I found a way to turn it down, but that also decreases the output. If anybody knows how to kill that speaker during the transmit, please leave a comment. I would really like to be able to turn that off. So if you got anything out of this, give us a thumbs up, punch that like button, and subscribe. I have some future amateur radio videos in the works. So 73s for now. If you got anything out of that video, you could help me by clicking that like button. And if you don't want to miss the next video, be sure and subscribe. And in the meantime, you could watch these two videos.